Coop, I appreciate it.
Yeah, happy to be here. Thanks for having me back.
Yeah, good to see you. Good. How could I not? It's one of the highest rated shows we've had so far.
Oh, that's really good to hear. I'm glad to hear people are loving science. It's
they
great.
do love science,
Yeah.
and they love. It's funny. I am a physics enthusiast. How would you classify me? Not a physics student, not even great at mathematics, but the concept of physics. It just it just engulfs me every time I go and I read or I watch a show on it. I just get totally into it.
It's really interesting, and like you're not alone, obviously, from like the show and everything, but there's a lot of people that fit into this category. And I think like maybe one way to think about it is before Galileo and Isaac Newton really started developing the mathematics of the subject. It wasn't called physics, it was called natural philosophy. And it was more about like noticing patterns in the world and trying to come up with like narratives and explanations for why the world is the way it is. And so
we don't do that anymore.
I mean, we do, but we cast it in the language of mathematics.
Okay.
And now it's more about modeling the world in the language of mathematics and less sort of like telling these like conceptual metaphors about the world.
Okay.
And so I think that like you would fall into this category of modern day natural philosophers, like people who are still super interested in understanding the cause and effect of the world and are also like very interested in trying to have some conceptual grasp of how it all hangs together, but you aren't necessarily wanting to like write down a differential equation that you put in like initial conditions and then output some kind of numerical prediction.
I think inside of me I may want to.
Maybe,
it's just that it's so damn hard without having the background.
And it's a totally different kind of exercise that requires a totally different set of tools and experience. And so I think it's cool that like there are sort of both of these things cohabitating and coexisting.
Okay.
And there's fruitful I think there's fruitful interaction between the two as well. Like there are actual physicists who go on to shows and they talk about stuff and
You're Hollywood physicists.
Yeah, they try and come up with metaphors and things like that. But then also like these metaphors that make their way through culture, those are the things that I, as like a practicing physicist, grew up with. Those were the things that shaped the way that I sort of saw things and thought about things. And so I think there is a symbiosis where like, we're coming up with the models, but like you guys are articulating the stories, and the stories are inspiring the future people who are coming up with the models, and the new models are the things that are pushing the stories into new territories. And so I think it's a good...
Well, let me ask you this before we get into... We're going to talk about gravity today, and I also want to talk a little bit about mathematics, not deeply, but the concept of mathematics and how it's a man-made construct. Am I right? Essentially.
It's a debatable thing, but yeah, I mean, that's...
Okay.
Yeah, we could get into that.
Well, but first I want to ask you, what was when you decided that science was for you? Like, when did that happen? Very early in life, and who were your quote unquote heroes in this field that drew you in?
Yeah. There's probably, I mean, like life is just this mix of random occurrences and interactions and people, and so any way to answer this question would be sort of like retrofitting a narrative onto my life that like may or may not be exactly how it
that's
went
fair
down.
enough. That's fair enough.
But if I wanted to kind of tell a story that tried to make sense of it, I mean, very early on, I was very interested in sort of like the act of creation, and like before I could actually like build things, I was into like art and just like sketching and drawing, and I would draw cities on pieces of like 8.5 by 11 paper that would connect via roads to other 8.5 by 11 pieces of paper, and I would stick them to my wall until my entire wall was like one giant city. And I was into like Legos and stuff, and then as I got older, I got really into building like actual physical material things. And me and my friends in the neighborhood would go out Thursday night and like trash night in Bethel Park, and we would just collect building supplies. And it started out as just a sort of like semicircle of bricks that we kind of made a little fort with. But this thing evolved over like 5 or 6 years growing up as like 7-8 year olds into like young teenagers, and it became like a multi-story building that had
multi-story building.
I mean, that only kids. Adults would have a hard time being on both of the floors and everything, but like as kids,
got it.
And it was only held together by by gravity. It was not. There was no nails. There was no anything, because this was literally. It never fell. I mean, there are parts of it that fell at times, and we would rebuild it. But like, yeah, we would basically use like tires and things like that to build up the sort of foundational structures, and then like thicker logs and boards. And we would find like corrugated plastic for roofing. We would find tarps. We would find, and then we eventually were big enough that we could like carry furniture that people were throwing out into our fort. And it was carpeted, and it had like couches inside, and
that sounds like a news story. Did they eventually did the newspaper or the TV stations get with you at any point in time?
I mean, it looked like trash. And so like the neighborhood, like the adults in the neighborhood weren't totally stoked about it.
I can imagine.
But we loved it, and like any kind of like contraband that a teenager would find, we could like hide out in our trash fort and everything. But I mean, yeah, there were like rusty nails, and like I'm sure nowadays probably we would have been taken away from our parents or something.
Probably.
But yeah, I mean so I always had that kind of going in, but I wasn't like academically motivated actually young as like a kid.
Really?
Not really. I mean, I did okay in school, it was fine, and I did okay in high school as well, but I was mostly just kind of interested in like projects and like video games and stuff.
Right.
I eventually went to college just because it felt like the thing to do, and I went for engineering because my brother went for engineering, and it was like I did well enough in math and stuff. But then it was really in college that like these doors to these more like conceptual worlds started opening for me, and I started learning about like, you know, I didn't understand modern physics, but that was starting to be told some of these stories about what quantum theory and stuff like that is, and, you know, string theory, things I had no way of understanding at the time, but like sounded really kind of interesting.
Probably pretty far out too.
Yeah, and so I was like this kid in this engineering class asking about all of these really far out things, and my engineering professors were just like, this isn't going to help you like build like a better steel I-beam, like stop. And so that's when I realized I wasn't really in the right place. And I had like a friend who I currently live with, who also was starting to get into these more sort of philosophical questions. We were both in the engineering program, and we realized it wasn't for us, and we left the engineering program, and he went into like philosophy and economics, and I went into physics and math. And we took a year off from Pitt and went to Oxford for a year, and that's where we really got all philosophical about things. And
those after school conversations between the two, you must have been unbelievable.
Oh, our dorm room was definitely, it was pretty, it was an interesting spot to be in. We didn't quite have the tools yet to really, in hindsight, to really talk about the things we wanted to talk about, but we sure tried, and it was really interesting environment. But yeah, then once we spent a year at Oxford and came back to Pittsburgh, that's whenever we started like a discussion club and reading groups, and we got really into our respective disciplines.
Was there that time, was there celebrity physicists? Was there celebrity scientists?
Yeah, I mean, like Stephen Hawking was writing books at this time. Elegant Universe, I think, came out right around then. But yeah, I mean, like, we were more into the sort of like academic side of things, though. Like, I was like finding like textbooks in the library and getting super into to reading those sort of things. And my other friend was more on the philosophy side, and he was reading like a lot of academic philosophy. And so yeah, I mean, there definitely were Neil deGrasse Tyson was on like Nova and stuff, like he was around
when he was a real physicist then.
yeah, but like we were not really going down that path. These sort of high production value YouTube video space wasn't really filled in at that point. YouTube was still pretty new because this is like 2006, 2007. And so we didn't quite get lured in by your like PBS Space Times and like things like that.
They're blending science fiction elements to the presentation now with hopefully more facts. And
I think that they definitely are like do their homework on there. But it's just like, I was definitely more interested in, because I was a math major as well, I was willing to like tread waters in that sort of environment.
Elegant Universe, was that Brian Greene's first multi-series? Was it him?
That was Brian Greene, yeah. I don't actually know if he did something before that. Fabric of the Cosmos. I don't know if that was before.
Yeah, I know. Okay. I'm a fanboy of that stuff. Yeah. So I think the Fabric of the Cosmos was 2010-ish, 11-ish.
Okay, cool.
But before that was the Elegant Universe, which I went back and watched in reverse.
Yeah.
And obviously, technical proficiencies were going in reverse. Like the show wasn't as glossy and slick as the Fabric of the Cosmos.
Yeah.
So it was a little disappointing as a consumer just watching it. But Brian Greene's directly responsible, for me at least, as a consumer of science, as someone keeping my interest and asking interesting questions.
Yeah.
That kind of made your head hurt a little bit. You know?
Yeah, that's awesome. I mean, and he also, I think, is instrumental in organizing I think it's called the World Science Fair or something. I've been to some events in New York
gone?
City. Yeah, because I went to grad school in New York City, and so they had
I've watched
events
them
all over the city.
Every year I watch. I'm not a
Holy
nerd.
cow.
I watch them all, like all the. And all the celebrity theoretical physicists are there.
Yeah, and even like
panel discussions.
Real ones too. Like the reason I went is because Steven Weinberg was going there to give a talk and do like a book signing, and so everybody was there to get their like Steven Weinberg's like History of Science popular book signed. But I showed up with like Quantum Field Theory Volume 2 textbook that he wrote, like
which probably impressed
ago.
Him more
And
because he probably was just.
He was excited.
Like
he saw that and was like, "Whoa, okay." And I was like, "Actually, this is my favorite section on spontaneously broken symmetries. Can you sign the top of this chapter?" And he was like, "That's a good chapter."
Okay.
So it was great. Yeah.
I know we're going down to more of a pop culture version of celebrities in your field, but everything kind of comes back to Feynman. Is it Richard Feynman?
Richard Feynman,
yeah. And I don't know a lot about him, but would you just talk a few minutes about it to kind of bridge like how he ushered in Neil Tyson deGrasse, Brian Greene.
Yeah, Neil deGrasse Tyson.
Neil
Brian
deGrasse.
Greene,
I'm sorry, Neil deGrasse.
Yeah.
Was Feynman the same era that Carl Sagan was, or was there a bridge there too?
Yeah, I would say those are two. They were definitely. I mean, Feynman was probably a little before. One, the Cosmos, the original Cosmos series that Carl Sagan wrote, that was probably 70s,
Yeah,
I
it was
guess.
when I was a kid in grade school.
Yeah, and Feynman was definitely around still in the 70s.
Okay.
But Feynman really, he got, did his PhD around World War II.
Wow.
And then as soon as he was part of the Manhattan Project.
Did not know that.
He was one of the lead theorists for the Manhattan Project. And then like all of the heavy hitters in physics at the time were working on the Manhattan Project, and they were all very impressed by Feynman, and so that's what helped him after the Manhattan Project.
Was he a young guy during World War II?
Yeah, during World War II, he had just finished his PhD,
Okay.
or was like during. I'm pretty sure he had just finished it.
Okay.
But it was right around the time when he was in his early 20s, mid 20s, and yeah, but he was like one of the few people that was willing to stand up to these like titans, like Hans Bethe, who was like this really famous physicist who did a lot of the early nuclear fusion type research about the sun and things like that. And he was one of the few people that would stand up to these titans and be like, "Nope, you're wrong," and like so people really liked him because he had a lot of balls,
he would have been after Niels Bohr and Einstein, right? That would have been a generation later.
Yeah.
Because those two had an iconic kind of battle, didn't they? Niels Bohr and Einstein.
Yeah, so Einstein was like born in the late 1870s, and so he was like in his 20s or so when he started writing a lot of these really impactful papers in the early history of relativity and quantum mechanics in like 1905, 06, 07.
Amazing.
Bohr was still a pretty young guy then too. He really kind of had his breakout around 1913 or so. That's when his big paper on quantum mechanics came out, the kind of early theory of quantum mechanics.
Which Einstein did not initially agree with or never agreed with at all.
No, so this is actually kind of I don't know how this got sort of like spread around. I guess it's like the fact that he didn't like some of the features of quantum mechanics, but I would credit Einstein for inventing quantum mechanics as much as I would credit any other physicist, actually.
Okay.
Yeah. I mean, the way the lore sort of plays out is there is this German physicist named Max Planck.
Yes.
And Max
like
Planck.
Planck time. You
Exactly.
hear the phrase
Planck
time.
Planck time, that he came up with all that. And Max Planck was basically trying to understand whenever something gets hot, it glows. And he was trying to understand like what the distribution of different colors comes out of glowing objects.
Okay.
The details are a little bit more, but we could just say that he basically was trying to understand how things radiate, light. And what he had to do in order to understand this problem was to kind of make an assumption that, well, I don't know if it's the light that is coming in these little discrete packets, or if you just have to sort of count up everything in discrete bits, or if the thing causing the light, which are these like vibrating charged particles, if maybe those things are in these discrete rotational modes or something. But something about that must be discrete in some way. And Planck didn't like this. He didn't think that it was like a really fundamental thing about nature. He thought it was just a quirky feature of the way he was calculating things, or maybe the mechanical system that was creating the light. But nonetheless, he had this hypothesis that like energy of the light was in some sense quantized in these little bits. And it wasn't until Einstein that really interpreted this correctly as being like, no, nature consists of these like quantized discrete packets of energy, and this should be true for, you know, electromagnetic radiation. It should be true for the like vibrating oscillators. It should be true for the way that like, you know, electrons in a metal absorb light in order to you know, acquire energy. So Einstein sort of conceptually put quantum mechanics into focus.
Yeah, we'll never get that from modern day lore. You don't get that.
You kind of see, and so then Bohr, like parallel to this, was thinking about like how atoms radiate very specific colors, and so he had to like make where the electrons are going around atoms to come in different places that are very specific, so that specific colors would come out whenever they sort of change their orbits. I'm glossing over a lot of historical details, but basically Bohr sort of came up with the sort of applied this quantum idea to atoms. And then it wasn't until like Heisenberg and Schrödinger in the 20s before they came up with a sort of correct mathematical way of looking into all this. And then it was like Einstein who sort of came back around, because Einstein sort of he was really instrumental in the founding of quantum mechanics, but 1905 is when he published special relativity, and 1915 is when he published general relativity, which we
10 years
when we talk about gravity, we'll talk about that, right? And so really for those 10 years, his baby was thinking about like the curvature of space-time creating gravity. And so he kind of like fell off not the map, although he still went to conferences and contributed papers here and there, but he kind of like stepped away from it a little bit to do this general relativity stuff. And then he came back and was doing a lot of instrumental things in quantum mechanics. And that's when he started to express that, like, there's something weird about quantum mechanics that doesn't...
Spooky action from a distance? Is that one of his phrases?
That, like, basically, like, nature seems to... You have to kind of give up something. Like, okay, it's non-deterministic. Maybe that's because of our ignorance. Maybe that's something that's just true about nature, that like it's kind of random. He seemed to be annoyed by that, but it didn't seem like that was like a deal breaker. This spooky action at a distance thing was a lot more important, I think, to him from what I've read. I'm not like a historian, but I've just like picked up random things from talking to folks, and it really seems like in physics terms you'd call it non-locality, but
is that what he had a hard time really agreeing to?
Yeah, he really was like, look, with quantum mechanics you really have to give up this idea that things are sort of like at positions in space. You have to think of space as sort of this like lower... It's not like a primitive concept, it's like a lower order thing, and that like quantum states could be extended infinitely far in space, and like those quantum states are singular objects even though they're extended really far in space. And so his Einstein-Podolsky-Rosen paper, the EPR paper, which is where he had this debate with Niels Bohr that's really famous about like him not liking, that was like about this sort of thing where he's like, look, you can create these like really non-local states in which you do something over here and it doesn't like send a signal over here, but you do know something immediately about that person's universe the second you do something over here, and that like sort of knowledge about that other person's universe seems to be instantaneous, and that just feels wrong. And so he was trying to like articulate this and poke holes and not necessarily poke holes in quantum mechanics, but basically say that quantum mechanics has some features that we and he articulated exactly how those features were sort of problematic. And so he would have liked, I feel like, the universe to be different, but I don't think, as a founder of quantum mechanics, I don't think I would definitely not say that he like didn't believe in it or disagreed with it or something.
I think there's a Hollywood version probably of what we saw in some shows as consumers of science, and I'm sure they put a spin on it. They were all photographed at this one conference together, but he wouldn't stand next to Bohr's, and they made an issue out of that.
The Bohr-Einstein debates were huge, and they were big in the scientific community, these debates as well. But the debate wasn't quantum mechanics versus not quantum mechanics.
I'm glad you cleared that up for me.
The debate was sort of like there were these conceptual features of quantum mechanics that like were being teased out at the time, and
because quantum mechanics has that element of to me, it had when I first was reading of it, it has a lure of magic to it, because talking about two particles that are connected, quantum entanglement, spinning, I guess, opposite directions, but the actions of each affect the other, but they could be 100 million miles away from each other.
Yeah.
That's just really hard for a non-scientific person to wrap your head around.
Yeah, I think kind of where what you have to maybe try and think about is that you're using language that's like, this guy affects the other, as if they're two different things.
Right.
And I think what it really is like, this is in the sort of mathematical description, quantum mechanically, when two things are entangled, you can't talk about them as being separate systems. You lose information that is in nature whenever you try and use this like idea of localizing this here and localizing this here, that they're more than the sum of their parts in some sense.
Got it.
And so you really have to expand your ontology, meaning like you have to expand what you can conceive of as existing to not just being localized bits of things, but these sort of extended objects in space. And that's why non-locality was sort of the theme of Einstein's
that took me a while. It took me a lot of, and I'm not and I won't say I'm the most disciplined reader, Coop, but it was a situation where I was reading, boy, I don't know if it was The Elegant Universe, if it was The Fabric of the Cosmos, the book, but I had to go back and read that chapter and a half over and over and over, because I just couldn't wrap my head around it. I mean,
it's very unintuitive. And this guy Bell, I think John Bell maybe, but this guy Bell in like the 60s, 70s, like he also, even better than Einstein, Podolsky, and Rosen, like articulated exactly what is like unintuitive about what quantum mechanics is doing. So these are called like the Bell inequalities, which are, I mean, basically what he kind of showed is that there's no way to, like, using classical metaphors, like pre-quantum mechanics metaphors, to try and describe what's going on. That like you can't just be like, well, you know, we just don't know what's really happening, and so what we're really seeing is some sort of statistical feature or like lack of understanding. That like what he showed is that no, nature is actually just more tricky than that. That like nature is not just, you know, hiding itself from us in the way that thermodynamics was hiding atoms from us. That like really once we understood atoms, we could describe how like steam engines and stuff like that worked as just the random motion of atoms, that atoms were just really small, so we didn't know about them yet. What Bell showed is that there's nothing like that going on with quantum mechanics, where something is just really small that we don't know about yet, and that would explain all of this crazy. Understood.
So
that's kind of the idea. But
we will get to gravity. But while I'm on the subject, what is the big argument, if I'm articulating it correctly, where scientists have been trying for decades to merge Einstein's theory of relativity with quantum mechanics and make them work in cohesion, or make them complement each other, or make them make sense together? Why are they so diametrically opposite? In theory, those two general theories. Why are they so opposite?
Yeah, so I mean, we kind of take it for granted now because we have such grandiose theories that explain the insides of stars and also how toasters work at the same time. But, you know, before the 1800s, science was like a patchwork of a bunch of different ideas. Like there was like, this is the best understanding of magnets. There are these weird rocks, you find them, you know, the Greeks knew about them in 600 BC, and like they kind of like seem to all be pointing in the same direction for some reason, and they repel off each other, and we can come up with like a theory of magnets. And there's other people who are like, lightning's weird and static electricity is kind of weird, and like you can kind of like use chemicals to make things that create static electricity. And so there's a theory of electricity. And then there was like Newton, who was like, everything's falling towards the earth, there's this theory of gravity. So science was really like, oh, that phenomenon, yeah, this, you go to this book for that phenomenon, and that book explains it. And then it was around like the 1800s where we were like, wait, electricity and magnetism, they can't be understood without like a larger coherent theory that explains how they interact with each other. And then interacting electromagnetism can create waves, And these waves are actually just what light is. And so optics is electricity and magnetism. So
Okay.
we started taking all these books, like the book on optics, the book on electricity, the book on magnetism, and putting them together into electromagnetic theory and starting to like patch all these things together. And this has been continued, and we've like slowly been patching all of our ideas together. And as you can imagine, as you start combining things, the number of different theories gets smaller and smaller and smaller. And now here we are, and there's like 2 books on the table. There's like space, gravity, like all this stuff, and then there's like the theory of like fields and particles and particle physics, like quantum field theory. And so this is like kind of the last step in a sense, is
marrying those two.
We got to put these 2 books together.
We've not been able to do that.
And we have not been able to do that, and it took us a long time to do the other ones too. So it's not like it. I don't think it's like we shouldn't lose hope that it's possible. But there are some conceptual reasons why this one is a particularly tricky beast.
All right, enlighten me.
Well, gravity, as we'll describe, and we can kind of go through it historically, but to jump to the end, the modern theory of gravity is that it's really a manifestation of space and time being a dynamical, curved thing, like something that has...
That's Einstein's work.
That's Einstein in 1915 publishes this paper that says, things push and pull on each other, but what gravity really is like something is literally just trying to move along in a straight line. It's just that straight is kind of tricky whenever you're on a curved surface.
Got it.
Right.
Got it.
And so that's the idea. That's the idea with gravity, and we could talk into more details.
Yeah.
But just to get into like your question about why it's so hard to put these things together, so gravity is about how the space and time itself is this dynamical thing, but particle physics says there are these things called quantum fields that live in space-time, right? The space-time is kind of the place where these things live. Right. And so once you tell me where these things live, then I could talk about what these fields are going to do.
Okay.
And so like Stephen Hawking, for example, was able to talk about quantum field theory and black holes at the same time.
Okay.
And so some people will be like, well, isn't that quantum gravity? Like black holes are Einstein's theory, and Hawking radiation, which is this fact that particles are created near the event horizon of black holes and radiating, that's quantum field theory. So why isn't that? But the point is Hawking said, well, I can do quantum field theory in any sort of space-time. It could be a flat, normal space-time, or it could be a curved one.
Right.
But it has to be like a fixed thing. Like it can't be changing. It just has to be a fixed thing, and then I could tell you what the quantum fields do.
Okay.
But if you really believe Einstein, you have to be like, no. Like the background that all of these fields are living in must also be a quantum object that is fluctuating and creating particles.
It's
and all
not
that.
Fixed.
Right. It's not a fixed thing either. And so what we haven't been able to do is figure out how to describe what these quantum fields do as they sort of bubble around creating particles whenever the sort of like world they live in is bubbling around creating, I guess, gravity particles. Like we have to try and understand what that even means. That the very framework of quantum field theory requires you to know what is sort of like in the present and in the past and and the future, and you have to be able to like consistently talk about all that.
Fixed variables, right? I'm guessing in the math there has to be fixed variable. It doesn't make any sense, but a fixed number, it has to be, right?
In the language of the math, the way that you describe your geometry, which is how you describe lengths and angles and all that sort of thing, that has to be fixed. Like the Pythagorean theorem has to be fixed and true.
Right.
But what Einstein says is that the Pythagorean theorem is actually something that changes near a rock that has mass. That like really the way you calculate the hypotenuse of a triangle given the 2 sides is different if you're near the sun versus near the earth.
Okay.
And so quantum field theory doesn't really know how to deal with that. And and what's important about that is, we have intuition about space, which is geometry, and the Pythagorean theorem and angles, but it's even more complicated because it's not just space that's dynamic, it's space-time. And so like what is the future and what is the past? Like these things are also dynamical quantum fluctuating objects in a quantum theory of gravity. And so that's really hard to deal with. And so like the most, I don't know, popular approach, you could call it the most successful, but like that's really debatable depending on who you talk to. But definitely the one that gets the most research money is string theory. And string theory kind of circumvents that by saying, no, the sort of like model for how to describe these quantum fields is still a nice, flat, non-changing space-time.
Okay.
It's just that whenever you have these kinds of particles that are, massless spin 2 in the math jargon, but in the sort of storytelling, it's just gravitons, that once these strings are able to oscillate like gravitons, that what the world looks like when you have a bunch of these gravitons around is it looks like it's some sort of curved dynamical world. And that the sort of background of the universe is still like a normal flat thing, but like because we interact with these like graviton particles, like it appears to us through our interaction with these other particles that we could describe the world as like this curved sort of thing.
Got it.
So string theory kind of says like general relativity is just kind of an illusion in some sense, but not like an illusion, more like it's a sort of like whenever you zoom really far out, this is the way things look. It's the sort. It's like an emergent sort of way of thinking about things. But it still has a nice. That's to be contrasted with this other theory called loop quantum gravity. Which,
is that more recent?
Loop quantum gravity is maybe slightly more recent. They all are sort of around like 70s, 80s, 90s.
Okay.
But loop quantum gravity isn't. It's probably the second most popular approach to putting these things together. Okay. But instead of taking quantum field theory as the primary thing and gravity as being this emergent illusion type thing, they take gravity as being the sort of like real thing that we need to understand and quantize. And so for them, there actually is a roiling sea of quantum foam that is at the sort of like smallest length scales, that really areas of the universe are like fluctuating things in some sense. So these two approaches are two different ways to take those two books and put them together. Now, separately, these books do a really good job. Yeah. Like general relativity, we're able to understand the universe billions of years in the past and billions of years in the future. We're able to understand the universe billions of light years away right here on Earth. It does an incredible job. Our GPS on our phones wouldn't work without it, right? Quantum field theory, these particle accelerators are creating terabytes of data every second, and we're able to understand every single bit of that data.
Is it true that quantum mechanics has passed every single test that's ever been applied to?
Yeah, there are no... That's what sucks. Like, physics is exciting whenever you have all these things you don't understand, where it's just like magnets, like what? Like, how do these things work, right?
Got it.
But no, the standard model of particle physics, which is our sort of like some understanding of how these quantum fields are bouncing off of each other, it's passed every test. I mean, there's every once in a while a little discrepancy pops up. The most recent exciting one is neutrinos. Are these particles that are like... They're all the rage at the moment. What's interesting about them is that they're very weakly interacting, which, like radio waves can go through this room and into our phones and things because they don't interact very strongly with like walls and ceiling tiles, but they do interact very strongly with metal. And so when you're in like a metal cage, like an elevator, you might lose signal in your phone. Okay, so things can be not very strongly interacting because of what material they're going through. Neutrinos are literally just not strongly interacting with any material that we know about.
But they go everywhere, right?
So there's as many whenever it's nighttime and neutrinos from the sun are going through the Earth and up through the ground at us, there's just as many of them going through us as when it's daytime and we're just directly... So the Earth itself isn't even stopping these things.
Are they moving faster than the speed of light?
No, that did make the news a while ago. So neutrinos, as far as we know, at least some of them have mass. The lightest neutrino, I don't know. I think there's really good reason to believe that it's also massive. So anything that has mass is certainly going slower than the speed of light. If it's massless, it's going the speed of light, and nothing is going faster than the speed of light. There was an experiment where we thought for a second neutrinos were arriving before they should have, and a million theorists started coming up with theories as to why, and I'm pretty sure the resolution of that was like a cord was like not entirely plugged in, and that like people weren't accounting for the fact that like they were using satellites that were moving fast enough for like special relativity to be incorporated. So there was just like a few and it was a really hard thing to figure out, and the experimentalists who wrote this paper were definitely like, we don't think these things are moving faster than light, but we dotted our I's and crossed our T's, and we have no idea why this is happening. So if anyone else wants to take a stab at it. I get it. And some people think that was an irresponsible thing, that they shouldn't have even said anything because it was such an outlandish claim.
Well, yeah, it muddied up the I mean, for scientists, they probably didn't muddy anything up for the casual observer, the casual person like myself with interest there. It was frightening because it wasn't explained, and you had all these theoretical physicists that couldn't explain it.
Yeah, and I don't know what to say about that because, like, on the one hand, I think it was good that they brought it up because it got the scientific community on the task of solving this problem.
Okay.
No one in the scientific community thought these things were moving faster than light. They all knew that it was a problem with the experiment, but they didn't know what it was, and so they just reached out for help, and they got it.
Got it.
But as soon as it gets into the news, all of a sudden it's like, could they be moving and then, like, this was like 5 years ago, and now 5 years later, someone is being like, now do neutrinos move faster than light?
Right. So and there was even PBS specials. There was even who is the English theoretical physicist that does a lot of BBC specials? There's a couple of them. One of them is
Brian Cox is a guy that I've seen.
He's great. I call him more like a rock star. This gentleman, I believe he's of Arab descent. He's got a
okay.
He's
I don't know if I know
excellent.
him.
And there's an older gentleman. I guess he's the senior of the British. He's done some great stuff too. But on this particular PBS special, they talked about neutrinos, and then they were conducting these tests in these mines, so they had to go so far underground because these neutrinos could travel that far. And there was, and I was so confused because how could something actually be traveling faster than the speed of light? They were actually saying it on the show, which was really
that's
not correct.
That's clickbaity. Yeah, so definitely, I guess I brought these things up because we were talking about the standard model doing really well at predicting things, so I'll tie that back into it.
Okay.
But yeah, so neutrinos, their average like interaction length, which means like if you shoot a neutrino through this table, how long does it take before it actually hits the table? Like it'll kind of be like a ghost particle going through it, and then it'll hit it eventually, right?
Okay.
The interaction length for a neutrino in lead, which is like one of the densest substances that are naturally occurring, is a light year. So if you shoot a neutrino into a light year length of lead, it'll on average like one time like hit the lead. So they're incredibly weakly interacting.
Interesting.
And so that's why we can go into mines, we can bury them in mountains. There's an experiment on the South Pole called Ice Cube, where we basically put sensors a kilometer deep into a glacier. And the reason we do that is because then we're sure that if we get hit by something, that it's a neutrino.
Got it.
Because everything else is going to bounce into the mountain or the eye of the glacier or whatever.
Got it.
And so that's just, those are basic, the glacier is like giant noise canceling headphones. In a
Got
sense.
it.
It's like getting rid of all the other stuff.
Got it.
But what's interesting that's happening right now, and I haven't been following it too closely, but I have been keeping an eye on it, is that they also have like, weather balloons that are neutrino detectors that are looking at neutrinos coming from above, sources coming from space, and also coming from below. And what they're noticing is that there's more neutrinos coming from the Earth than there should be. And so
why would that be?
And so what some people think is like, well, that means that like there must be a neutrino source in the Earth that is like creating extra neutrinos. And this is like getting dark matter people really excited.
Okay.
Because one explanation would be like dark matter is like neutrinos in the sense that it's incredibly weakly interacting, and there's tons of it going through this room right now, going through our bodies, and we're not even feeling it. But maybe dark matter particles are like hitting something in the Earth and annihilating and then creating neutrinos the same way that fusion reactions create neutrinos in the sun. And so we're hoping that maybe this is like a direct detection of dark matter or something like that.
Which that'd be a big,
which
big
would be
event.
huge. It would be the biggest news in a long time. Yeah. So that's very exciting. But the one thing to keep in mind is because these things interact so weakly, that means you have very small number of data points. Like one of these experiments, it could see like 8 neutrinos in a year. Yeah, and so you might have like millions of gallons of water as a target, and then you might see like 8 neutrinos. And so like it's really
that has to be almost impossible.
Exactly. So that's why like statistical fluctuations can really trick you in neutrino physics because you just don't have a large enough number of data points to be able to to be able to learn about averages. Like in particle physics, I don't know if you've heard of the 5 sigma thing.
I have not.
So basically, like in particle accelerators, we smash things together and look at what comes out.
Right.
And what comes out, because of quantum mechanics is kind of random in some sense, but it follows some patterns. And it's by understanding these patterns that we could say that, like, oh, a Higgs boson must have been created in this collision.
And that was at CERN,
and that,
the most recent.
That was at CERN.
Fermilab was before that.
Yeah, Fermilab had the Tevatron, and it just wasn't quite high enough energy to be creating these things. And it wasn't until the Large Hadron Collider in Switzerland, France.
Apparently, it's not powerful enough, right? Because they're going to build another one.
That's yes, the Future Collider. Yeah. I don't know. I mean, I guess we're kind of straying about, but like just a few 2 cents on that. I like never want to be someone who goes out in a public and says that we shouldn't do like some science thing, but like I really am skeptical of the scientific merit of this
based on expense
as a new machine. Yeah, I mean, like, okay, like if you look at what governments spend money on, it's like I think it's still kind of worth it. But if you do believe that it's some sort of zero-sum game where that money would be spent somewhere else in science, I do think there are better things to be working on in science right now than this. The reality of the situation is that's not really how it works. Like, it's not like there's a fixed pool of science money and then we just sort of like allocate it in different places. And there are definitely benefits that have nothing to do with science to these collider projects. I mean, like my brother is a radiation oncologist. He uses particle accelerators to cure cancer.
Got it.
So like, there's definitely reasons to be excited about CERN invented the World Wide Web. Like, there's reasons to be excited about it. But I think the scientific reasons are a little bit shaky. Yeah, I mean, there are a lot of like puzzles in quantum field theory that we still need to work out about the Standard Model, but it's not like there's like a glaring problem that like if we just had this machine we would figure it out. Like, you know, in the late 1800s people thought that electromagnetism was like this medium that light was sort of like disturbing, and that's why you had electromagnetic waves. Like, you have water waves because when you disturb the surface of water, it propagates waves. And so this is called the ether, and there was a pressing question, which is like, is the ether, if we're flowing around in this fluid, what direction is it going, right? And so like, you know, 1887 or so, Michelson and Morley built a device to basically measure the flow of the ether, and that was like a very pressing question. It was a very succinct experiment to answer that question. Whereas like this Future Collider, it's just kind of like, well, there's some things that like feel unnatural about like the Standard Model that like maybe suggest that just around the corner there might be something new. And we understand the Higgs, but like we could understand it a lot more better if we had a little bit more precise measurements, which we would get if we had like a bigger machine.
Is it a matter of speed and crashing? The power of these crashing particles will be increased by speed, so this collider would accelerate faster.
Exactly. Yeah. I mean, E equals mc squared, and so if you want m, you need
got
E.
it.
And so if you're trying, I mean, the Higgs boson is, I think, something like 125 GeV, which is heavy. It's a lot heavier than you know, the proton and the neutron are around 1. And so we basically are trying to make something that is 125 times heavier than
Is there any danger to mankind in messing around this way? I mean, because again, novices like myself who read things, you have some people who are fearful that things are going to happen, and science poo-poos that. Oh, that's ridiculous. I mean, you hear everything.
Yeah. I mean, to be real, we should leave no stone unturned. And so, like, I don't think there are scientists who just like straight up dismiss any sort of like problem that a particle accelerator could create, and that's not exactly right either. So that you should look into like what could happen if there is some kind of new physics that would like create something that could be kind of destructive. Like a famous example is like, what if you create like a black hole?
Right, that's what they're
like,
scaring the public with.
Exactly, but what you need to think about is like these giant machines that create these collisions at even higher energies happen all the time in the upper atmosphere. That these particles,
they're naturally occurring.
They're naturally occurring. The reason we have to build this machine is because we want it to occur in a very specific spot at a very specific time over and over again. It's not because they don't happen ever. But another thing we got to be careful of is like, well, whenever these collisions happen in the upper atmosphere, they happen in a direction roughly at the speed of light. And so if an ultra high energy cosmic ray created a black hole in the upper atmosphere, it would be moving through the Earth at the speed of light.
it.
And so it would just fly right through the Earth. And so
Got
maybe
it.
it does happen, but they're going the speed of light. It takes maybe 50 milliseconds at most for light to go through the Earth. And so
Got it.
those things are gone. But what doesn't happen is you never have two cosmic rays coming at each other and then hitting each other and just stopping.
Got
Right?
it.
And that's what we're doing. That we're
On
putting-
Earth.
Yeah. So the particle accelerators are creating things that are more or less at rest
Got it.
in the frame of the Earth,
Got it.
as opposed to going the speed of light. And so that was a real question. And so people calculated this, and what they saw was that nope, we're still good. And so
Okay.
scientists took it seriously, and they worked out the math, and they were able to quantify their unknowns in a way that they felt pretty safe.
We've turned up the velocity of the Hadron Collider since from the time it opened, which
Yeah.
I think was 13, 14, something like that. When did it open? 12?
Yeah, probably around, I think 2012 is when we actually found the Higgs boson, so it must have been open a little bit before that. But yeah, around then.
But technology has helped us even increase the velocity,
Yeah.
but it's not enough.
We had phases in the design of the Large Hadron Collider. Be superconducting magnets are getting this better every year, and so by this year we should have new technology to upgrade the magnets, and by this year, so it constantly gets little upgrades here and there. But at the end of the day, you are limited by the size of the ring. What's hard about this is that when you take particles and you accelerate them, and so I don't just mean make them go faster, I mean when you change their direction. When you're in a car, you don't feel going 70 miles an hour on the road. If you have cruise control on, you're relaxed. When you're in a plane going 500 miles an hour, you don't feel it.
Right.
What you feel is when A, you step on the gas, and then you feel it on the back. B, you step on the brakes, and you throw it forward. That's speeding up and slowing down. But C, when you go around a turn, then you also feel it, right?
Right.
And so if you take charged particles and you go around a turn, then what they do is they radiate. And if they're radiating, then that's creating heat. But what's keeping them going around in a circle is a superconducting magnet at 200 degrees below zero. And so the hard part is that you need to make what do we do on the highway? If we up the speed limit, we got to make the exit ramps have bigger turns, right? And so this is what you have to do with particle accelerator, exactly. That you don't need as much, centripetal force. They don't radiate as much if you have bigger rings. And so the bigger the ring is, then
the bigger it needs to be, the more space, the more miles, everything.
Yeah,
what are they talking about for this
tunnel.
new one? Have you heard any
100
specs?
kilometers.
100
It's
kilometers.
at about 26, 27 kilometers in circumference now, and so they're talking about 100 kilometers. So yeah, that's here to Grove City or something of tunnel.
And CERN right now, it encompasses multi-countries. It's a
It's on the-
multi-country effort.
Yeah,
but
it's on the border of France and Switzerland, so
Okay.
it goes underneath both. The particles they spend a few nanoseconds in France and a few nanoseconds.
If you were
in
a betting
Switzerland.
man, do you think it's going to happen?
I think if it does happen, I think it'll happen in China. China is talking about doing this as well, and I just feel China kind of has more to gain, just because if they did build it over there, then particle physicists would want to use it, and they would go over there, and institutions would start.
Got it.
They have if they want to be internationally serious as the West in terms of their contributions to theoretical physics, then it would really help them if they had this machine. So I don't know. I mean, the expertise and stuff is in the West and with CERN and everything, and Europe has money. They could probably do it, but I just feel I don't know. If I was a betting man, I would say that it doesn't happen.
Interesting.
That we probably end up building a linear accelerator. I think in Japan they're talking about a straight line one that also could do precision Higgs measurements. But if they do, if a giant $20 billion 100-kilometer ring gets built, I kind of have a feeling that China, that loves very quickly building really giant things, would be the one to do it. And just allocating resources for large public projects is a little bit easier whenever you have total control over your economy, the way that a command economy China has. Whereas for Europe, you need to form partnerships, and there's a lot of problem with
the
international
EU has to get involved, and there's
EU has to get
politics involved with
There's
it.
and especially with what's happening in the UK and in the United States, there's more sort of isolationist vibes politically happening.
No question. Well, at least now, anyways.
Unifying. Yeah. Hopefully that turns around. But
I agree. I agree with you. All right, let's get to gravity.
Oh, gravity.
Gravity again. And I know that could be a 20-hour conversation.
Yeah, it's like
But
a several semester class.
I can imagine.
Yeah.
So, but I guess my question is going to be: there's been a lot of news about gravity the last couple of years,
Yeah, totally.
which a lot of it's confusing to the person who's not a theoretical physicist, someone just reading the news or watching a TV special. Maybe we can talk a little bit about that. But why gravity was confusing to me as a child was that it was always taught as an assumption, like there's gravity.
Yeah.
We learned about other things, but the gravity was the constant. And was it taught that way in the 70s and 80s because we just didn't really understand it? We just accepted that gravity was a variable and you just dealt with it because we knew it as a variable only?
Yeah.
I don't know.
So, I mean, I feel like we've gotten a little better at like cosmology, which is like the gravity of the universe, like how the universe is expanding and contracting. But like general relativity by the 60s and 70s was like pretty well fleshed out. But like, yeah, gravity, one thing why I think it's like kind of alluring to people is because it's like, I could tell you about neutrinos, but it's like, I could tell you facts that are cool, like 60 million neutrinos go through your fingernail every second, but it's like, okay, so what? But like gravity is something that like I deal with every day, right?
Okay. And
so like gravity is the one thing that's like, it's all over the place. Like even when the power goes out, the gravity's still, in my house. So gravity has an interesting history. One, like I don't know if it's a misconception or if it's more of a joke, like there's memes about it all the time, is that like Newton invented gravity or something, and so you see memes of people like floating.
I've seen that meme before.
It's pretty good. It's
a good meme.
But yeah, one thing I'd like to clear up since we're here at the public is that like Newton didn't even like discover the concept of gravity. Like obviously people knew a lot about gravity. Like there were military engineers who made it their job to understand the trajectory of cannonballs and finite ships. So gravity was extremely well understood. What Newton came up with was the universal law of gravitation. So like things falling, that totally makes sense.
Based upon weight, they still
Earth.
fell at the same. That was his thing. They fell at the same rate.
So that's also true, but that's not what I mean by the universal law of gravitation. But we'll get to that too. That's called the equivalence principle.
Okay.
Well, okay. We'll get into it.
Okay.
But so no, what this was that gravity isn't just a thing about rocks here on Earth. That gravity is a thing about like the universe at large.
Right.
And that like that glowing orb up there that like has something to do with like, I don't know which, it was like Diana or something, whatever Greek god had to do with the moon. But that giant orb up there, like that thing is doing what it's doing because rocks fall on Earth. And like all of these things we call planets that are like making these weird epicycles through the sky, this red one we named after Mars and this kind of yellowish one we named after Venus, those things are making that weird shape they're making because rocks fall here on Earth. And that's the universal law of gravitation, that like the sort of harmony of the solar system is actually just a pretty mundane effect of a bunch of rocks floating around, attracting each other, the same way that rocks fall towards the Earth,
I get it.
That, I mean, it seems kind of funny. It's like almost obvious, but like Newton was kind of the first one to be like, okay, the Earth is a sphere, which we've known since like 200 BC. Like Columbus didn't figure that out. Like we knew that there's a spherical thing. So everyone's like attracted towards the middle of it because there's people on all sides of it and they're all standing on the ground. What if you had like something really far away, you dropped it, it would like fall and hit the Earth. Well, what if you kind of like threw it pretty fast in this direction? Well, it would sort of fall, but it might not hit the Earth, right? If it's going fast enough, it might miss and it might fall down here. But like then what does it want to do? Well, it still wants to fall towards the middle, and so it'll keep doing that, but it might miss it again, and then it'll end up here, and then that just might keep repeating, and all of a sudden you start having circular and elliptical orbits. And so it was, Newton was the one who was just kind of like, wow, this like things pulling towards a common center, that could explain why you have the sun, which is this giant thing, and then you have all of these other little rocks that are all zipping around in circles.
Because we thought we were the center of the universe initially, right? The Earth was.
Yeah, so it depends on how far initially we want to go back. But
Copernicus.
Okay, but I'm talking, that was already 1400s. Like there was like plenty of science before that. Yeah, so initially, of course, we didn't even understand the concept of the universe. But actually, the Greeks thought the sun was at the center. And so like Aristarchus, who was way back, he was like a mentor of Archimedes. So we're talking like 300 BC, Plato time. He not only was like the sun is at the center of the solar system, he correctly predicted that it was Sun, Mercury, Venus, Earth, Mars, Jupiter,
incredible.
Saturn.
That's incredible.
But then it was kind of people like kind of like Christian influence sort of mixed in there, and we wanted to kind of get back to the center of the universe again for like kind of philosophical, theological reasons. And then Ptolemy came up with this really comprehensive theory in his book, The Almagest. I never know how to pronounce it. Almagest, Almagest.
Almagest, I think. Yeah.
So it's just this really famous compendium on the solar system, and he put the Earth back in the center, and then that was sort of like. And Aristotle also was a big fan of the Earth being at the center too. So it was really, I guess we should really trace it back to his influence. But anyway, so the Earth was in the center for a while, and then we get to like the 1400s, 1450 or whatever, and Copernicus is like, let's put the sun back in the middle. That actually like kind of makes these things work out pretty well.
Right.
And then and that still wasn't quite that. Actually, kind of a little known, not very well known fact. Ptolemy's model had gotten so. Just there were so many variables that you could tune, like finely tune how all these epicycles worked, that you could match the data perfectly with Ptolemy's model, and that Copernicus's model was wrong because it said the planets moved on circular orbits, which is not true.
Right.
So actually when Copernicus came up with his idea, yes, kind of the phenomena were more simply explained by Copernicus, but the data was wrong. Copernicus was more wrong than Ptolemy in terms of the data.
Interesting.
And so if you were like a real scientist who believed in data over like aesthetic reasoning, then you would say like, sorry, Copernicus, like you made a prediction and it was wrong. Ptolemy's right. But it was really kind of sticking with the aesthetics of the idea that like Kepler eventually corrected Copernicus to add these elliptical orbits.
Okay.
And that's whenever it became sort of more accurate.
Okay.
And then Kepler's laws were what Newton had to try and explain. That was like, Newton, you have this idea that like gravity is what causes the planets to move in the orbits they move on. Great, but like you need to recreate Kepler's laws. And that's what he did. He mathematically came up with a theory where he said object A and object B, they attract each other with the following formula. And then he invented an entire branch of mathematics called calculus to show that that formula would imply Kepler's laws and would imply the usual trajectory of planets around.
Does that fascinate you at all, or being a scientist, does it like you see the logic of how they got there? Because to me, based upon what they had to go on, they created it themselves. They created mathematics.
Oh yeah, I mean, like if you think about it, like there are these little dots at night that seem to be in the sky. Some of them are kind of just like doing this overall rotation, throughout the night. But some of them are sort of like every day in a different place, and they're kind of like wiggling around. And literally by just staring at those dots for 2,000 years, we invented the thing that allows us to do, fluid dynamics and material science. And like calculus is needed to be an engineer. Like if you're trying to build a bridge, you need calculus. And so it was literally just by looking at those dots and being like, what the hell is up with those dots? Like that's like what inspired the sort of conceptual framework that led to this thing. And we kind of lose that today because of the fact that you don't really see many of these dots, and we have our own artificial dots called light bulbs that are in our houses and stuff. Right. But like something that really was a kind of an eye-opening experience for me. Me and my friends back in like 2010, we got this empty piece of land in Tennessee. Like we just bought this cheap because it's cheap to buy just acres of land down there. And
especially back then.
Yeah, totally. And one cool thing is it was on the eclipse path. So we got to go down there for the total solar eclipse in 2017. Cool. But anyways, when we go down there, there's very little light pollution. I mean, it's way out there in the boonies in Tennessee. And sometimes we'll go down.
Explain what that is, because I discovered that too, traveling, and I was amazed.
Yeah.
As opposed to like here you see very limited in southwestern PA, but you go to the desert, you travel south.
Yeah, it's amazing.
Totally different. The sky looks completely different.
Yeah. I mean, one thing to keep in mind is that the sky is not transparent entirely. Like, if the sky were transparent, you'd look up and you'd see the sun, and then you'd look to the right of it and you'd see a star, right?
Got it.
Because like there'd be nothing in between you and the star, nothing between you and the sun. But during the day, you don't see stars.
Right.
You see the sun, and then everything else, you see this kind of weird blue haze. And what you're looking at is the sky. That the sky actually, it allows some light through, and it scatters some more light. And different colors scatter by different amounts. Blue happens to scatter a lot, which is why on average your cones in your retina, say, okay, that's like bluish. There's other colors in there, but it's mostly blue. And so that's also true at night. Whenever light is coming from the ground and it's going up, it also scatters. And when it scatters in every random direction. And so it goes into your eyes. And so
light pollution?
That's light pollution in some sense, right? Okay. And stars, it's amazing we can see them. Like, our eyes are pretty awesome, right? It's amazing we can see them because they are so far away, right? These things are like, the ones we could see in the sky are close enough that they're like only like maybe hundreds of light years away, but they're still hundreds of light years away. So it's incredible we could see them, but we can just barely see them. That's a really important fact. And
it's old light we're seeing too. Right?
Oh yeah, that's light from, millions of, or I guess probably hundreds of years ago in that sense.
It's amazing.
If when you look at the Andromeda galaxy, that's like millions of years old. But the important fact is that, like, if the sky is scattering any light, then that's going to wash out any little bit from the star.
Got it.
And to kind of explain why we can just barely see stars are not white. Like, all of these things we see in the sky are a bunch of white dots. Stars are colorful. They're red, they're blue. They're different colors because they're different temperatures, and different temperatures emit different colors. So the night sky should look like a giant rainbow of dots.
But it doesn't.
But why does it just look like white dots? Well, we have two different kinds of cells on our retina. There are rods and cones. Mm-hmm. And cones see color, and rods don't see color. They're just kind of grayscale. Rods are really sensitive, and they're mostly like whenever something's sort of like moving, or it's like at night, and those are for survival. It's really good to have super sensitive things.
Okay.
But like for like purposes of like, finding fruits or like mates using colorful feathers and things like that, the cones, they don't need to worry about sensitivity. They just need to be like, I need to be able to tell what color this is. And so the cones are nowhere near as sensitive as the rods. And so starlight is in this special place in between that's bright enough that our rods can see it, but not bright enough that our cones can see it.
Got it.
So the night sky looks black and white for everybody.
Got it.
Now, there are some stars like Betelgeuse that are big enough and close enough that you could tell they're kind of reddish.
There's a hue to it.
Yeah, and so you could tell. But anyways, so let me get some water.
Absolutely. We have noise pollution. I knew it as a kid. I went to a summer camp in New Mexico. As a child, a Boy Scout camp, and one of the most amazing things besides the camping was just looking at the sky at night. It looked so amazing, compared to what I was used to here in southwestern Pennsylvania.
It's really beautiful. And to kind of tie back to the Tennessee thing, the point was that if you spend just a week or two where like the only source of light you have for like 5 hours out of your day is a fire in front of you, and like all this light up here, you just naturally, half of your vision is this space. And you just naturally start to notice patterns. You naturally, like, I know very little about like positional astronomy. I'm an astronomy teacher, but I mostly teach about astrophysics, not kind of like constellations and stuff. But like, by the end of my trips to Tennessee, I could pretty accurately draw you sort of the main sort of like shapes of stars, just because that's all I had to look at for like 5 hours a day every day. So it totally, that experience helped me realize that, like, before there was electricity, like half of your time, the only thing you could see was this crazy pattern in the sky. And
natural light.
So just like during the day, you want to try and understand plants and animals and people and all this sort of stuff. At night, what is there to understand about your universe but this crazy blanket of patterns and stars? And
Coop, is that why you see a lot of the massive telescopes are built like in the hills of Peru? They're built like in places where they go up very high. It seems like they're trying to get above mountains when they build them.
Yeah, so there's multiple things you're trying to look for. One is, of course, you don't want any light to go up and come back into your telescope, so you want to get away from light pollution, so you don't want to be near New York City and stuff like that. Right. Two is that the atmosphere isn't something that's linearly getting thinner. What I mean by that is when you go twice as high, it's not like you have half as much atmosphere.
Okay.
If you get twice as high, you have way less than half as much atmosphere. That the atmosphere gets thinner exponentially.
Okay.
So like 99% of the atmosphere is within the first sort of like 10% of what we would call the like height of the atmosphere. And so when you go up, 15, 20,000 feet, on top of these huge, volcanoes in Hawaii and these huge mountains in the Atacama Desert and things like that in Peru, you're above most of the atmosphere. So
Interesting.
You don't have to go to space. You're like getting pretty close to
You're in space.
Yeah. So that helps. The second thing is that, you could see if you kind of look through a water bottle and you look at light is going all sorts of different directions. Like that source of light is stationary, but if I put a water bottle in front of it and move the water bottle around, that light's going all over the place. So water actually bends the path of light.
Right.
And what is in our atmosphere but tons of water vapor? And so that's why you want to be.
I never thought of that.
That's why you want to be in the desert, and you want to be above.
It never rains in the desert.
Yeah, so there's no humidity in the atmosphere to deflect the direction of the light. Because what astronomers are trying to do is they're trying to say, where did that light come from? Because if they know sort of like where that light came from, they can reconstruct the shape of star clusters and things like that. But if light is just sort of like coming from all different directions because on its way through the atmosphere it's getting deflected by water molecules and stuff, you can't recreate the picture. It limits the resolution of the sky because the light is sort of a single point is creating a pattern that's all over the place.
Got it.
So the size of that pattern in the best places on Earth, which are high in the desert in South America and on mountains in Hawaii, and volcanoes in Hawaii, the size of that pattern, the best you could get is an arc second. Have you heard of these things?
No.
Okay, so what a sensible thing to do would be to sort of say like a circle has 100 degrees, and then we could talk about like 1/10 of that and then 1/10 of that, and use the decimal system,
right?
The way that the metric system uses the grams and centimeters and stuff. But angles are old school. Angles are geometry, and the Babylonians were into that. And so instead, we use this Babylonian system, which is sexagesimal, which is not base 10 but base 60.
Okay.
So, the British were into base 12, and that's why you have like dozens and things like that. Shillings are 12.
Yep.
But the Babylonians were into base 60. So they would count up to 60 before they would go into the next slot, right? And so that's why there's 360 degrees in a circle.
Got it.
That's why there's 60 minutes in an hour, 60 seconds in a minute. But we did a similar thing with the circle, where a 60th of a degree is called an arc minute.
Okay.
And a 60th of an arc minute is called an arc second.
Okay.
And so an angle that is a 60th of a degree is called an arc second.
Okay.
And that's about as tiny of a region from Earth that you can see in the sky. You can do better than that in space because there's no atmosphere at all.
Right.
And you can do better than that with radio because you can... Well, basically, the atmosphere is more transparent to this kind of light. And also, you can do this thing called radio interferometry.
What is that?
So basically, why does like a mirror like help you see things from far away? The reason is because the shape of the mirror takes light from a bunch of different directions and it concentrates it together in order to like create an image of what was far away.
Almost kind of like a mirrored telephoto lens, right?
Exactly. So you could have a parabolic mirror, or you could have a parabolic lens that refracts the light all into the same place. So so that's the point. That's how optics like helps you see small things, helps you see things far away, is that it takes all that information and it puts it together by using the shape of the mirror, right? So what you can do, like why that works, is because the shape makes sure that like the light that came in and hits the mirror, it goes to the same point at the same time, so that you aren't getting like different light from different parts at different times. But what you could think of in principle is like, why do we need the mirror at all? Why don't we just all over the Earth collect light and then just recombine it as if we were on the face of a giant mirror?
Okay.
And the answer is, well, light has a really short wavelength, and so if your recombination is off by a little bit, then like you can be really wrong about how you're recombining it. Also, the information that you get out of light doesn't include the things you need to do that recombination. The way that light detectors work wouldn't quite work that way. But radio waves are big enough,
right? And
you get different kind of information from a radio wave detector that you can actually do this.
Okay.
And so we can build Earth-sized telescopes by basically putting radio interferometer stations all over the Earth, and then just take all that data, put it on a hard drive, send it to a supercomputer, and then the supercomputer reformulates it all. And that's how we saw the event horizon of the black hole. By doing this, where we had an Earth-sized radio telescope, because the resolution, it goes like 1 over the size of the telescope. So if the size of the telescope gets bigger, the resolution gets smaller. And so
Got it.
Yeah. So let's talk about this thing about things falling at the same rate.
Okay.
Because Aristotle, he was a brilliant sort of like philosophizer, and like came up with these like amazing metaphors and ideas, and he told the best stories about how like nature like should be. But he wasn't a very good experimentalist, or rather he didn't really see experiment as being the ultimate like adjudicator of truth. Like, experiment isn't the way you learn more about things. You use your head to learn more about things, and like, you know, if you have a really good idea and the experiment's wrong, then like that's the experiment's fault, not my fault.
A little arrogance in there, right?
Yeah, I mean, it's just kind of like, again, if it's more about like philosophy, then it's not really about what nature's saying. It's more about how we're telling the story.
Is that a constant battle too? Philosophy versus science?
I think that, yeah, and within physics, I think there is this battle of like, how far ahead of experiment should you go?
Okay.
So this is where like there's a lot of criticisms of string theory in particular, because like some of our experiments are going like into regimes in which we could never or some of our theories, are going into regimes in which we could never imagine doing an experiment to ever like test this thing. And so some people are like really like, this is now different than what we usually call science, because if you're talking about stuff that we couldn't even in principle like measure, then that's that we're back to Aristotle.
Yes. How do you validate it? Then that would push toward philosophy then.
Exactly.
Theory.
Yeah, totally. And what some people argue is like, well, no, like this has always been the case. We've always had to be ahead of where experiments are at, because it's only through like going into these like dark forests of thought that we actually stumble upon these sort of like, so for example, like Einstein, when we get a little further along in gravity, we'll talk about general relativity, and like you would have thought probably between 1905 and 1908, his early general relativity work, if you were like an experimentalist and you were sitting in an armchair with Einstein and he was explaining the curvature of space and time, you would just be like, this is ridiculous. Like, you're never going to be able to like measure that, like who, blah, blah, blah. But then by, you know, the time he published, he realized that there was extremely measurable things about it that were not intuitive at the outset. I think that's what string theorists are hoping, that like really there's going to be some falsifiable experimental things that come out of this. We just aren't mature enough in the theory to understand exactly what they would be.
Or the technology, maybe?
The technology isn't there. Technology is a really good example. You were talking about gravity in the news, and that's because we've detected gravitational waves.
Let's get there. Let's do gravity, because I feel like I could take you 1,000 different directions.
It's true. Yeah. Okay. So let's talk about gravitational waves. Let's talk about Einstein.
Absolutely.
So why are things seem to be falling at the same rate, right? And like I said, Aristotle, he said this wasn't true. Heavier things would fall faster. And he never bothered to like do the experiment, right?
Okay.
And fast forward like 1,700 years, between like 300 BC and 1500 AD, we get to Galileo, and Galileo actually is like, presumably he did the experiment, but nonetheless he got the right answer, which is that like, nope, things just fall at the same rate. Some things catch a little bit more air than other things, and so they look like they're going slower because we're in this medium of the atmosphere. Right. But things fall at the same rate.
But no, a feather wouldn't fall the same rate as a brick, though. There's got to be some kind of variance there, right? I mean,
no, if there wasn't the air, they would fall.
The air is okay.
Okay. So it's the point that like right now, like we feel like there's like the ocean and then there's the land, and we're up out of the ocean, but really we are at the bottom of 100-kilometer ocean, and there's just another deeper ocean that has a more dense liquid.
Understood.
We have this fluid called nitrogen and oxygen that we're little crabs crawling around in the bottom of this 100-kilometer sea, and then there's another deeper sea that like has like a more dense substance that we call water.
Got it.
But that's really, the ocean is really an interface between two fluids. It's not like a fluid and then out of it. So Galileo really understood this, and so he was like, yeah, of course, like if you're in the ocean, like if you're in the water, like if there's a current, then all of a sudden and things start moving, and you wouldn't base your theories of physics based off of like being in the water, because like how would you explain how a rock just picks up and starts tumbling whenever it's raining?
So the theory is, if you're talking about dropping two objects, regardless of their weight, we're assuming it's in a vacuum.
In a vacuum, yeah.
Okay.
And so like the moon, for example, it isn't big enough to maintain an atmosphere, and so famously, I don't know if it was Neil or one of the astronauts, there's a video of him dropping two things on the moon and they both hit the ground at the same time. And we've done this experiment on Earth too with the vacuum. But so this is very interesting. And Isaac Newton, he was like, okay, I have this theory of gravity. It depends on your mass. How much you attract something depends on your mass. And then I have this theory of motion, which says like if there's a force acting on you, how much will you accelerate? And that also depends on your mass. And for Newton, this two things falling at the same rate was kind of not that interesting. It was like gravity pulls you according to your mass. How much you get accelerated by a force depends on your mass. Mass is on both sides of the equation. They cancel out.
Got it.
So there's just no mass in the equation. Your acceleration is independent of mass.
Okay.
It's not that gravity pulls the same on everything. It's that gravity pulls harder on bigger things.
Yeah.
Exactly the
mass.
amount it has to, so that way they fall at the same rate.
Understood.
Right? But Einstein did not think that this was just like some mundane thing. Einstein was like, that's really weird. That gravity, like your attraction to something, is a completely different phenomenon than like how hard it is to get you moving through space. Right? Through space and time. Like, so to him, he was like, wait a second. If everything is experiencing the same motion due to gravity, then maybe gravity is not an external thing that's pushing and pulling on stuff. Maybe gravity is actually a feature of the background space and time that we live in, right? If it's like everything is sort of falling at the same rate, then like you could kind of think of it like they're all in the same background, as opposed to thinking of it like they're each getting pulled a different amount, but it all cancels out, so that way they're exactly accelerating at the same rate. So this is called the equivalence principle. This equivalence between gravitational acceleration and just sort of like normal acceleration. That like, I mean, we're kind of going down a slightly different path, but Einstein was very interested in the fact that there's this equivalence between gravitational mass and inertial mass. Like, one of the things that would mean is that if you were standing on Earth, you would feel like you were being pulled down to the Earth. If you were in space, but in an elevator, you would feel like you were being pulled down onto the floor of the elevator, and that there wouldn't be a sort of physically distinguishable thing you could do between those two situations. No experiment you could do to say, oh no, actually this is gravity pulling me. I'm not. If
you couldn't differentiate between the two, right?
If you were in a locked space elevator and you couldn't see outside, there's nothing you could do inside of that elevator to tell whether you were actually just at rest on a giant planet and you were in an elevator, or whether you were in the vacuum of space and you had rocket boosters underneath you causing you to accelerate.
I heard it, and let me see if it's the same analogy. Like either Brian Greene or one of them used in one of their programs that if you were an ice skater spinning, but you remove the ice, you remove the space, you remove everything from there, and you're still spinning, but in relevance to what? Is that the same? Is it the same up the same alley?
So this is something that I still struggle with today, which is a little different, but it is related. It's something that like this guy Mach and like Mach's principle.
Heard of that?
He was sort of like had a similar sort of question, and Einstein tried to answer this question. He like Mach is like a sort of like philosopher of science. But yeah, basically what Newton says is like, okay, motion you can't really tell. If you're going at a constant velocity, there's nothing you can do to tell it. Like I can't, if I'm on an airplane going 500 miles an hour at a constant speed, I can't do an experiment on my little tray table that would tell me that I'm moving at 500 miles an hour. Right? If I'm on the highway in cruise control 70 miles an hour on like 76 and I'm like sitting in my lap, I can't do an experiment to tell I'm moving that fast. I can look at other things and say with respect to that, but there's no experiment that could say that I'm completely at rest. And of course not, right? Because really, airplanes are moving in an atmosphere on a planet which is going 66,000 miles an hour.
Yeah, something to, as respect to something else.
Exactly. Yeah. And so, but what Newton realized is that like, well, rotational motion is not like that. If you have a bucket filled with water, if you spin that bucket, the shape of the water goes from a flat surface to a parabola.
Right.
And so like if you were an ant that was like floating on the surface of that water, you could tell whether you were spinning or not, even if you were spinning at a constant velocity.
Got it.
And so this was something that like Einstein was like kind of curious about, and he sort of wondered, was like, does somehow the fact that you are spinning relative to the rest of the universe create this parabolic shape of the water?
Mm-hmm.
If you were truly the only thing in the universe, would you have that parabolic shape? And so like Einstein's theory of relativity actually has features of it that like when you spin, you create a sort of like spin to like space-time as well.
Got it.
That like
I understand that.
gyroscopes, whenever we put them in orbit around the Earth, actually process differently because the Earth is spinning.
Got it.
And it's causing the gyroscopes to process differently. So that's
Wow.
like kind of cool.
That's very cool.
And I think that's kind of more what that's related
Okay.
to. But it all is part of this thing of like gravity is really just a manifestation of space-time. The analogy I always love to give to try and understand how gravity could just be a curvature of space, which I might have talked about in the last show as well, is that this really simple thought experiment, which I don't know if I read this somewhere or what, but it's like seems very obvious once you think about it, which is like, okay, the Earth is a sphere. Imagine the Earth was a perfectly flat, perfectly frictionless sphere. So it's a giant ice ball, right? Snowball Earth, like in the past, the Earth was a giant ice ball before,
Right.
so let's say it was again. If you're on the equator with somebody and you start moving with a constant velocity, you're both going at the same constant velocity, and you're both going like parallel to each other.
Okay.
So you both head north, right? You're
Okay.
at the equator, you both head north, right? Okay, you're going at a constant velocity, so you don't
Right.
feel anything.
Right.
That person is going at a constant velocity. He doesn't feel anything. So to you, it's just us right now. You're just at rest. I'm at rest, you're at rest. We're both moving north, but the Earth is totally flat and featureless, so we can't tell.
Right.
We don't feel anything. But what starts to happen, right? What starts to happen is we slowly start getting closer to each other.
That's what I thought.
Right? And why do we
That's
get
what I
closer
thought.
to each other? Because, well, if you follow a line of latitude or longitude, north, you hit the North Pole, and if you both start at the same speed, you hit it at the same time.
Right.
So from our perspective, we feel nothing, right?
We're getting closer
But
together.
yet we get
though.
closer.
Right.
And the rate at which we get closer is changing. At first, we don't get that much closer at all, but we accelerate closer.
It's
and closer to each
exponential.
other.
Like,
Well, yeah, I mean, it's probably some kind of like linear function, but at the end of the day, it's just like how there's a 1 over r squared force dependence.
Got it.
So what we would say in this reality where we live on a sphere is, oh, there's a force of attraction between two people. It is a force because it causes an acceleration. Because we don't get closer together at a constant rate, we accelerate towards each other.
Right.
We don't feel it. And if you were a mountain and I was a mouse, if we both had that same velocity, we would, a mouse would fall towards a mountain the same rate that like a cat would fall towards a mountain that an elephant would. And so it's independent of mass.
Yeah, mass
in
is
some
irrelevant
sense,
there.
right?
Okay.
We just experience an acceleration.
Okay.
And so in that thought experiment, it's very clear that the phenomenology, the features of gravity, could simply be explained by just saying, oh yeah, we're on like a curved surface.
Okay.
And so Einstein kind of ran with that and was like, in order to really get the correct 1 over r squared kind of force dependence, in order to get circular, like elliptical orbits and everything, how would geometry have to be affected by mass in order to create the force due to gravity? And that's what his theory of general relativity is like, how do you unpack this metaphor of the ice planet just everywhere so that everyone is being attracted to everyone else, and that all of us independently are creating the curvature of the ice planet that we need so that we all attract each other all at the same time. And that's what general relativity is. It's how matter curves space-time so that we all feel nothing yet appear to be attracted to each other.
Right.
Because you don't feel gravity. Like, you feel the floor stopping you from falling to the earth.
But is, from a quantitative standpoint, gravity's rather weak, isn't it?
Yes, it's really weak in the sense that, like, I don't feel so big, but I am enormous. I am like 10 to the 20, maybe 6, 10 to the 27 particles. You are 10 to the 26, 10 to the 27 particles, but we don't feel an attraction to each other at all. Right? Whereas, like, the only way I feel an attraction to something is if you have The Earth is 10 to the 24 kilograms, which is like 10 to the 27, 26 particles, right? And so that's like 10 to the 40, 10 to the 50 particles. And now I'm starting to feel an attraction to it.
Got it.
And it's not that much of attraction.
Right.
We built airplanes and helicopters. We're able to beat it. We built rocket ships.
Absolutely.
To contrast that with other forces, like let's say my hand is made out of protons and electrons and neutrons, so some positive particles, some negative particles. This hand is some positive particles, some negative particles. If I took just 10%, so like 1 out of every 10 electrons in my hand, and I just removed it from this hand and put it on this hand, right? This is now slightly more positive because that balance got upset a little bit. There's more protons than electrons.
Right.
This one's slightly more negative. It's got extra electrons. If you hold your hands apart like this, they're going to attract. Because this is, and we're not talking about like 10 to the 50 particles. We're just talking about like 10 to the 20 particles, right? So they're going to attract. And the question you could ask yourself as a physics 2 sort of question is, what's the force of attraction? Could you hold your hands apart? Could the strongest man in the world hold their hands apart? Could you hold them apart if you chain this hand over here and chain this hand over here? And the answer is that the force is on the order of the weight of the moon if you were to try and hold the moon on your shoulders. It's something like 10 to the 22 newtons or something like that.
So even the slightest mathematical change,
just a little imbalance. So electricity is insanely strong, and that kind of makes sense when you think about it. That it has to be that much stronger than gravity because I'm able to stand up, which means a thin layer of molecular bonds that make up like my shins along any cross section of my legs are able to hold up my body. You know, there's a tiny little layer of molecules that are holding up my body, and there's 10 to the 24 kilograms of the Earth pulling it down.
It's incredible.
And yet, those little molecules win.
Yeah.
Right?
Yeah.
So gravity is not weak in the sense that, like, a comet hitting the Earth could kill us all, but it is weak in the sense that, like, you know, if you just look at a particle that has some electric charge and it has some gravitational charge, namely it has some mass, that we don't even care about gravity. Particle accelerator experiments, they pretend like gravity doesn't even exist because like 2 electrons, they attract each other because of gravity, but they repel each other because of electricity.
Got it.
If you do the math, they repel each other, one with about 42 zeros after it times more than they attract each other.
It's incredible.
And so you don't really, so that's why they call gravity a weak force, right? It's because you need a planet worth of stuff in order to just feel it, and it's not even that strong at that
Understood.
point, right? Yeah.
One of the confusing things to me always was, especially once I started being a fan of physics, was why was gravity never talked about in terms of, at least I never heard it, in terms of a force or a particle. Was it a wave or is it a particle? What the hell is it? Yeah. And it only was the last 10 years or so when the word graviton became part of the vernacular that I thought maybe it was a particle. I was really confused on that.
So this is another reason why it's really hard to put these 2 books together, to put the general relativity book and the quantum field theory book, because the things that exist in the quantum field theory book are these sort of quantum fields. And like, quantum fields are mathematically tricky, and so sometimes it makes the most sense to describe them as creating particles, but really the way that they kind of interfere with each other and the pattern of particles they create is kind of wave-like. And so like a quantum field is both sort of wave-like and particle-like.
It's both.
Yeah, it's really neither, but like at times it expresses itself.
Does it ultimately depend whether you measure it or not, or whether you're looking at it or not? I mean,
I mean, we interact with the sort of particle-like excitations of this wave-like field. And so, like at the end of the day, it is sort of like that. But yeah, it's not like, is it a particle or is it a wave? It's like, no, it's a mathematical object that is neither of those things. But for the natural philosophers out there that are trying to tell a story with metaphors, sometimes the particle metaphor is the appropriate story to tell, and sometimes the wave metaphor is the appropriate story to tell.
Got it.
Now, that's what's going on with quantum fields. With gravity, they're saying, no, the effect of gravity is because space and time is curved. Like, it has nothing to do with particles or fields. It's just that, like,
back to Einstein's theory,
the stage we're walking on is wiggling. And so,
got it.
And so that's what's going on with Einstein's theory. So quantum field theory would like to say, no, the stage is also made of particles, and like we're walking around on a bunch of particles that are like oscillating, right? And so, but what people that are like loop quantum gravity people, what they would want to say is like, no, there's something fundamentally different about gravity. And so that's why, particle physicists would love to just say graviton, and it's just a bunch of gravitons. And string theory too would just say that like a string can oscillate like a graviton, and that's why string theory has gravity in it.
Well, graviton sounds like a particle to someone like myself. When you hear gravity broken down into gravitons, it sounds like we figured out it's made out of particles, which that blows my mind to conceptualize that, to turn gravity, this force that... this confusing force, at least to someone like myself, now all of a sudden we've broken it down into a particle. Because graviton, the word, doesn't it even insinuate particle?
Yeah, a graviton would be a particle in this picture. But be careful, because that's the same with electricity, that it's really the photon that creates the electric force.
Okay.
And so the standard model...
I thought photon was attached to light. I thought light was the...
Light is a photon. That's right. So light is what is responsible for the electric force in some sense.
Okay.
So this is something that's really hard to grasp about quantum field theory, that forces are really just... things are experienced forces because things exchange particles with each other. And that like the particle that is exchanged, you could attach to the force that we're talking about. And so photons are the force carriers of electromagnetism. There are these things called W bosons and Z bosons that are involved in the weak force. There are these
I know that. That was the weak force, and I know a little bit about that.
Yeah. But it's the same kind of thing where it's like it's a force, but like it's really, you could say that particles are responsible for that force.
Okay.
And so that's what the graviton is supposed to be, the particle responsible for the force.
Is that a recent discovery, the graviton?
So Einstein in 1915 wrote down this theory of gravity being this dynamical thing that space and time is able to kind of fluctuate and bend and contort and all this stuff.
Into space-time.
Right? Exactly. But what that would mean is that it is a medium through which things should be able to propagate. Like if you have like a sheet of fabric, if you perturb it, then it creates these little ripples. In water, it creates little ripples.
That's the fabric of the universe.
Exactly.
Right?
But it shouldn't space-time be the fabric of the universe, this thing that ripples. So
Got it.
Einstein worked it out, and the answer was yes, that, okay, there should be gravity ripples that sort of like propagate away. And he worked out how strong these gravity ripples would be, and he was like, we're never going to be able to measure these things. Like, to be able to measure, these ripples are so weak, so what would a ripple of gravity be? It would mean that geometry would be rippling, that how you measure the distance between 2 points would fluctuate. If you had a roller between 2 points, that would fluctuate.
Got it.
And so you could ask yourself, well, how much does geometry fluctuate from a ripple that would be caused by some astrophysical thing like two rotating black holes or something like that?
Right.
So Einstein worked it out and was like, we would have to be able to measure distance to an accuracy of 1 part in like 10 to the 21, 10 to the 22, right? So he was like, this is impossible. This is an interesting theoretical thing that there are ripples of gravity, but we're never going to be able to measure them.
Okay.
That's like the width of an atom is 10 to the minus 15 meters. And so this is 1,000,000 times less than that. If you had like a meter long, if you're trying to look at a meter stick, you'd have to be able to measure a meter stick to within 1,000,000th of the nucleus of an atom. And the nucleus is already 100,000 times smaller than the atom.
Right.
And so Einstein was like, obviously this is never going to happen. But he was wrong, as Einstein often is. And 100 years later, in 2015, we actually did this. We took a 4-kilometer
by technology,
with
right?
Technology, technology that he didn't know was possible. So we actually saw these ripples. Okay, so this is equivalent not to seeing gravitons. This is equivalent to seeing light for the first time.
Okay.
And so in some sense, it's an even bigger deal. It's like if all of a sudden there was a blind civilization, and people could feel the electric attraction between things. And they eventually could come up with a theory for how electricity worked and a theory for how magnetism worked. And then they're like, if there's electricity and magnetism, there must be these sort of fluctuating electromagnetic waves. But how could we measure a fluctuating electromagnetic wave? Well, we'd have to build this device, blah, 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 and this amounts to a camera. And then all of a sudden, they're like, holy cow, there's these fluctuating electromagnetic waves everywhere. And they tell us about stars and planets and all this sort of thing.
Right.
And so that's what happened 4 years ago, is that we finally opened our eyes to gravitational radiation. And gravitational radiation is a lot weaker than light in the sense that it's like harder to measure
Okay.
it. But it has some advantages.
Okay.
And the main advantage is that light comes from positive and negative charges fluctuating a bit, causing the electric and magnetic fields to fluctuate a bit to create these little things, right? But the problem is that like not everything is transparent because things are made out of charged particles,
Right.
and these charged particles can absorb this
Understood.
like oscillating thing, right? And that's why like I can't see outside of this room. Now, different kinds of light are transparent to different kinds of things, and so a radio wave could see out of this room, but a radio wave couldn't see through the earth, right?
Okay.
An X-ray can hardly even make it like, so
Right.
some waves like can't even make it in between us because the atmosphere would absorb it. Right?
Okay.
Famously, our atmosphere is stopping infrared waves from leaving, and that's like why carbon dioxide is so dangerous. But gravity doesn't have positive and negative particles. Gravity only has positive particles. There's no such thing as negative mass. Even antimatter has positive mass, right?
That I know.
And so what that means is that you can't block gravity. You can't like put up a shield. That'd be nice if you could, because then you would, airplanes wouldn't need so much fuel if you could just put something underneath them.
So we can't manipulate it.
Yeah, like you can like manipulate it in the sense that like you can like move objects around that have gravitational fields associated with them, but you can't like stop it. Like I couldn't screen it with something, right? I couldn't shield myself from gravitational radiation. And so you might think, well, that makes it like less useful, but it makes it better at seeing things.
Okay.
Because like you can only, for example, the early universe, at some point the universe was so hot and dense that like it was just filled with a plasma that was not allowing light to propagate through it. That like light would go a little bit and it would hit a charged particle and get absorbed. But at that point the universe was still transparent to gravity, because everything is transparent to gravity. And so gravitational waves we would be able to see further back in time to before the time when the universe became transparent.
Got it.
And so we could see through things that we can't see through with light. We could see past points when the universe was transparent.
Still not all the way back, though.
Not all, well,
We're getting
I
close.
don't even know what all the way back means exactly. Like, who knows? But yeah, so anyways, that's very exciting. Now, you said something about gravitons, though. So what would seeing a graviton be? So in history, we've seen light before we saw photons.
Right.
So what does it mean to see a photon versus see light? Well, whenever I look at a light bulb, my cones and rods, my retina that's being excited, it's getting hit by like 10 to the 20 photons. Okay, so it's really the aggregate effect of 10 to the 20 photons that are creating this. We didn't understand the sort of particle-like feature of light until we were able to sort of dial that down, until we could actually see like single photons at a time, right? And actually manipulate and send
We
single
did that
photons.
100 years ago. That's the split test, right?
The double slit.
And it blows my mind that we had machinery that could get atoms down to individual photons.
It's pretty incredible.
It is, and to do that test, we did it 100 years ago, roughly.
Yeah, it's amazing. But we were able to do that because of how strong electromagnetism is.
Got it.
That even a single photon could like hit our detector and cause it to like blip, Now, gravity, as you know, is 10 to the 42 times weaker in some sense. Right. And so we just barely saw two 30 solar mass black holes like colliding. Just barely, right? So imagine trying to dial that down until you could see just one graviton. And so that is the challenge of quantum gravity, is that like we can just barely see the brightest things in the universe as far as gravitational waves go. Like, how the heck are we going to create our double slit experiment with a single graviton? That's probably never going to happen. But Einstein said the same thing in 1915, right?
We may never see it. We may never see it.
Yeah, probably not, but hopefully we can help people get there in the future. So presumably gravity is a particle, just like everything else. That would be the sort of way that string theorists and stuff like to think about it. But there's also another alternative, because gravity is so intimately tied to what is past and what is future and everything. It might not play by the same rules that other particles do, and it might, that's what loop quantum gravity is all about, is to actually like treat the fabric of the universe as a fluctuating thing, and what that would mean for physics.
Because it's only positively charged, though, man cannot manipulate gravity. Well, we may manipulate it, but we cannot eliminate gravity.
Yeah.
Like NASA would probably find it very helpful to be able to eliminate gravity for training purposes, I would imagine, alone.
Yeah.
Astronaut training, right?
And there's also something that's sort of like kind of even more conceptually problematic about it manipulating. Because if you could remove gravity, you could take a like 100-ton boulder, you could put it in a gravity shield, you could put it up really high, and then you could get rid of the gravity shield, and you could smash it into like a giant spring that generates a ton of electricity, and then you could pick it back up with 0 energy, and then drop it, and then it would create a ton
that
of
changes
energy.
mankind
So
if you manipulate
you
that.
could create like a perpetual motion machine and get
Right.
energy for free.
Right.
And the reason why that's like possible is because like gravity is intimately tied to energy, because E equals mc squared, right? So energy is mass, but like mass is gravity. And so turning off gravity is in some sense very akin to like turning off energy in some sense. And so like there's more theoretical problems than just there's only positive mass. Like it would break physics if you could like turn off gravity in some sense.
It's only positively charged.
Yeah, that like you don't this doesn't have like negative 12 grams of water, but it might have negative 12 coulombs of charge in it. Right.
Wow.
So yeah.
But the average person on the street who pays a little bit of attention considers gravity a particle now because of the graviton. I can't tell you how many times I've heard that from people when the discussion comes up. And
yeah, I mean, the paradigm of particle physics has been extremely successful, and so like your default position, if you don't know anymore, should be that. I think that's very reasonable. Like dark matter too. There's a lot of different theories about dark matter that have nothing to do with particles. But like, if I'm going to put money down in Vegas, I'm going to say it's like a neutrino. It's a particle. It's very weakly interacting, so it's really hard to actually like collect in a detector or something. But just like neutrinos and quarks and all that, it's just a particle floating around. And so that's probably the prevailing theory of dark matter, is that it's just a weakly interacting particle, and the task now is to try and detect it. And to try and understand its properties by measuring it. But there are people who are like, no, dark matter is pointing to a bigger, like, that we don't really fully understand gravity. That gravity itself is actually a little bit different than we thought. So,
let me throw this at you. I think it's related. Was the Kepler was a physicist? They named They named a telescope after, right? The Kepler telescope. But that was the one that we launched into space and put it in orbit, right? And it's still there. We're still using, or I think we're still using it, right? The Kepler.
Kepler. This was the exoplanet telescope, right? I think so. I'm pretty sure. Yeah.
Was Kepler also?
That's why a lot of exoplanets are called like Kepler 2A and things like that. Yeah. And it's, I believe. Yeah, one of my best friends in graduate school was like a big exoplanet scientist, and so he was working a lot with this Kepler data, and I believe it has a certain number of motors in it that allows it to be able to point at things, and enough of them broke that it didn't have enough axes to rotate about to point correctly. But the engineers found a way to use the motors that did work plus the solar pressure of the sun's like solar wind to allow it to tilt the other way, so that they could still point it. So like it wasn't able to rotate in 3 dimensions. It could maybe only rotate in a plane, but like they could rotate such a way that like the solar wind would like push it in the right direction and then rotate again.
Unbelievable.
So that was pretty cool. So that was like the last I heard about a couple of years ago, but it might there's new ones coming out now that are gonna supersede.
How does gravity relate to, let's say, Alan Guth's inflationary theory?
Yeah,
because we're still using that as fact, I'm assuming, for parts of it anyways.
Yeah, inflation, it definitely explains the data in like kind of a nice way. So
things are moving away from each other at an increasingly fast rate.
Yeah, so that's like the dark energy thing. But that's a little different. It's very similar, but it's a little different than what Alan Guth and those. So these people were trying to explain the very early universe. Like why, if you kind of look on very large scales, the universe doesn't seem to have any sort of overall curvature to it. It seems to be just sort of very uniformly distributed stuff everywhere. And so the question is like, what's sort of like flattened out the universe. Like, you would think that quantum fluctuations would cause this thing to have more curvature. But Alan Guth's theory was like, well, if it spent some time inflating where it was like exponentially growing, any kind of curvature would be like completely flattened out. And so this was his way of explaining this.
Okay.
And it also has some other features about how like it explains what the spectrum of quantum fluctuations imprinted on the cosmic microwave background would look like. So there's other sort of interesting, predictable things that it's passed a lot of tests that way. But what you're referring to is the modern day fact that like the universe is expanding and its expansion is accelerating.
Yes. Still,
yeah. Well,
in the theory that eventually it'll start to slow down and at some point stop and then contract. That's the theory, right?
So yeah, that's what we don't know. So yeah, cosmologically, our best picture is that the universe underwent a rapid period of expansion, and that explains some things that are kind of puzzles about cosmology, and so we say that's probably true. What exactly is the inflaton, the particle that created inflation? We don't really understand. There's some theories, there's some like good guesses. String theory likes to say it has some ideas. Okay, but then it sort of stopped undergoing its inflation, and all the energy that was in the inflaton field eventually turned into like protons and other sort of things.
Okay.
And then it sort of went through a couple different phases where like first like a lot of the energy was, most of the energy density of the overall universe was packed up in radiation, and then as it sort of expanded, the radiation sort of gets diluted really fast.
Well, cooled, right? In
yeah,
theory.
so that's a very intuitive thing where it's just like as things expand, they cool. But like with radiation, if your box gets bigger, it gets more dilute because the volume is bigger.
Okay.
But it also gets more diluted because you get redshifted. Your wavelengths go from being short to long. And so you lose energy in two different ways. You lose energy density because your box is bigger, and you lose energy density because your energy is less.
Okay.
And so the radiation diluted away first, and then the universe became matter dominated, where it was really the matter that was important, the energy.
And we're still in that phase, right?
So actually, since we've turned over into the dark energy dominated phase.
Okay.
So dark energy is some fixed amount of energy density that doesn't change as far as we know. That's why we call it the cosmological constant. But
that's a long number, huh?
Yeah.
That's a graphic of that number. And
totally.
Nothing can change in that, right? If one numerical value at any point in that fraction changes, everything's different.
Yeah, we think it's constant. There's been some recent stuff that are like, ooh, has it been changing a little bit? It's hard to say. So that's kind of some exciting stuff that we don't really know. But anyways, this stuff doesn't get diluted at all. So in the early universe, it wasn't really important because the universe was so dense and packed with all kinds of radiation and matter. But as the universe expands, it'll expand to the point where now the dominant source of energy density is not the matter because the box got too big. It's definitely not the radiation because the box and the wavelengths got too stretched.
Right.
But now the dominant form of energy is actually just the sort of background energy density of the universe called dark energy. And if you work out what general relativity says about background constant energy density, it says that when you measure lengths with rulers, they'll just keep getting bigger and bigger and bigger, and they'll get bigger and bigger at a faster rate. And so we're in this dark energy dominated era of the universe where everything is accelerating away from each other. And that acceleration is a function of how far away the thing is. Mm-hmm. And so there is a point where if you go far enough away, then you'll be receding away faster than the speed of light.
And that gets to the point where there was a theory I read once that if all these objects keep moving away from each other at the rate that they're going and continue accelerating, at some point the universe will become completely dark. There'll be no light. There'll be just void of anything measurable. Not in our lifetime, not in maybe millions of years from now. But the point is,
a very long time from now.
It would be light wouldn't be able to reach each object.
Yeah,
is that right?
Because once you go outside of this distance where you're receding faster than light, you could send light toward me, but the space in between us would be expanding faster than the light is going towards us. And so that's why we say there is a size to the observable universe.
Got it.
It's not that we think the universe has a size. We don't even have the ability to comment on the size of the universe. Mm-hmm. What we do have the ability to comment on is based off of cosmological measurements, we could say the rate of acceleration of the universe by looking at stars at different distances and supernova at different distances. And we could say, well, if the universe is really accelerating at this rate, stuff that is like 14 billion years away is like, in distance, right, light years away,
Understood.
is far enough that we would never be able to talk to them anyways.
Right.
And so in some sense, they're not in our universe. Like,
so they don't exist.
yeah, they're like causally disconnected from us, that there's no cause and effect that could interact our two spaces. So they might as well just be like the fairyland or something,
But how does that jive with the theory that there's going to be contraction at some point? If we're going to write off the fact that we don't.
Right. So we don't know exactly what's causing. We could put a number in our equations and call it the cosmological constant, but we don't have any sort of understanding beyond that. Like, in principle, something like string theory or something like that might be able to tell us what that number is.
Okay.
But we don't have a theory right now that tells us what that number is. And so for all we know, maybe that number is a decreasing function of time. And maybe that number starts to get smaller and will get so small that maybe the universe will become matter dominated again. And then it'll start to contract. And as it contracts, the wavelengths get shorter, and then it becomes radiation dominated. And then it really starts contracting. And eventually we end up in some sort of like big crunch type scenario.
Would the contraction potentially be at a much faster rate than the expansion? Or are they tied together where the contraction must be at the same speed as the expansion was?
So, I think that it would be different. And one of the reasons why I say that is because, like, nuclear fusion is a sort of non-reversible thing.
Okay.
That, like, yeah, my intuition is that, like, there have been processes since the beginning of the universe where hydrogen fused into helium and created, like, light and neutrinos and stuff, that if you ran the clock backwards, things would look different because of this fact. That
We
like,
probably can't imagine. We can't imagine that even scientifically, right? Because
well, maybe somebody can. I don't. Yeah, but I don't. Yeah, I mean, there are definitely people who talk about the universe as like a thermodynamical, like an adiabatic engine that's like expanding and contracting, and so there are people who think about this question. But my intuition is just that probably the contraction would look different because the contraction would not be the same as the expansion run backwards. Like the expansion was like you had all of these like charged particles, and then the protons captured electrons, and these things kind of smashed together due to gravity and lost their electrons as they smashed together more, and then the protons smashed together and formed helium, and the helium smashed together, and then, but when you run the clock backwards, like all of a sudden there's like all this iron floating around and all this and there's all this like starlight that's like filling the universe that wasn't there at the beginning. So I don't know. I would think that the contraction rate would be slightly different than the expansion rate. But the devil's in the details there.
Okay. Well, the concept of order and lack thereof of order, does that play into it at all? Like there's an order to the expansion, the natural order, but the contraction would not be the same uniform. There would be no order, it'd be disorder, right?
Yeah. So you're kind of getting us into a rabbit hole, which is
I'm used to doing that.
So you're starting to, and I was thinking about
entropy, right?
Entropy.
Entropy,
yeah. So like
right.
I was like on the car ride over here, I was like, are we gonna end up talking about entropy? And so I started trying to think about a metaphor for entropy. Entropy is like the thing that like is the bane of physicists' existence when like crossing the natural philosopher physics boundary.
Okay.
Because to us, entropy is like a tool that we like calculate. We know how to use it,
right?
But the story of entropy is like an incredibly complicated thing.
Yeah.
So yes, the universe is more disordered in a sense than it was before, and so that plays a role. That entropy is higher, and so when you're expanding and contracting, those look like symmetric processes, but for both of them, entropy has to be increasing, and there's a sort of direction to time that says increasing entropy. So yes, I mean, but yeah, what entropy is like a very kind of tricky thing to kind of get into, because to me entropy is like you have some sort of collection of states, you have some sort of way that you describe the universe, and you might bunch a whole bunch of states together into one box and give it a label, and say like this is like a box of mass blah 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 with some temperature blah blah blah, and then I could ask the question, well, how many different states did I put into that box that have the same like large factor macroscopic parameters? How many microscopic states are in that macroscopic box? To me, that's what entropy is like counting the number of states in that box. But the way it's sort of talked about is it's sort of like randomness has more entropy versus less entropy. But that's really just because if, let's use a concrete example. If I have a deck of 52 cards and I have a little box that's like, okay, here's full houses. Okay, there's actually only 4 in this box. There's like the spades, the hearts, right? And then there's this like box called like flushes, and there's a bunch of them. There's all sorts of different ways you can collect like a flush. There's a box called pairs, and there's a bajillion different 5-card hands that have pairs. And so I would say like this is high entropy because there's a lot in this box. And then there's a box that says like you didn't get anything, and there's the most number of random 5-card hands in that one. And so I would say like least entropy, more entropy, more entropy, more entropy, most entropy. But for like a way to describe it, you would say most ordered, less ordered, less ordered, less ordered, completely disordered. But we kind of have to be careful. Like the reason why it worked out like that is kind of how we define these boxes. And there's some situation in which like things that look more ordered actually have more entropy.
Interesting.
Like for example, if you have a whole bunch of pencils randomly in a shoebox, and then you take that shoebox and you just sort of like jiggle it back and forth, the pencils will all line up with each other, and they'll form like a nice straight line. And so in some sense, that state has a higher entropy than when they were kind of randomly disordered. And it's not higher because it's more disordered. It's actually more ordered in a sense. It's higher because now they aren't as jammed together, and they have more ways in which they can move. And so there's sort of more available microstates that
I get it.
Fit.
Yeah, I get it.
See what I mean? So that's, and the universe is evolving into states of higher and higher entropy just because like if you do a bunch of random stuff, you naturally find yourself in boxes that have the most kind of different possible ways to be, right? But
if you say you have a chalice, a glass chalice, and then you take a ball peen hammer and you break that chalice and glass goes everywhere. Is it possible in science that whole event could run in reverse?
Yeah.
Is that possible?
It is possible, right? Because what happens is like you shatter the glass, it falls, it hits the ground, and creates all of these
shards,
sound waves in the ground. That when the shards hit the ground, they create what are called phonons, which are really just like sound waves. And so like the ground just like all that like kinetic energy from the glass shards hits the molecules on the ground, and all the molecules jiggle into each other and jiggle away. Right? It is possible that if you had the right sound waves in your ground, that you could jiggle them all at a pile of glass in just the right way, so that when the molecules on the very surface got hit by all those sound waves from the bottom, they'd smash into the glass shards, and those glass shards could all fly at each other in such a way that they like hit each other at just the right angle, so that all of those molecular bonds between the
have
glass
we run tests to do this? Have we done this yet?
This would be completely impossible in practice. This is just a sort of like thought experiment. But the point is that there's no laws of physics that say that this can't happen. That like it's only an environmental sort of coincidence that like you don't see coalescence of these phonons all rising up from the ground, striking an object, giving it exactly the right like momentum, and like everything would have to be completely perfect for that to happen.
Like running through that wall. If I tried to run through that wall 100 million times, maybe 100,000,001, things would line up physically correct to do it. It isn't going to happen, but it is possible. Is that right?
Yes, but that's a different thing.
Okay. What is that?
But yeah, so this has to do with quantum tunneling.
Okay.
Which is the fact that you are like a collection of quantum objects, and quantum mechanically, there's really no such thing as a wall. That there's really like energy barriers that that a particle has to try and get over to get to the other side. And in this case, it's like there's a repulsive force between the particles in the wall and the particles in your body that like they don't want to occupy the same space at the same time. But quantum mechanically, they can. It's just like statistically, the odds of you tunneling
It's a mathematical
through this
equation.
is small.
Odds-wise.
Exactly. But it's really important. Like, the sun wouldn't shine if it wasn't for this. The sun is not hot enough and dense enough to actually take two protons and get them close enough together to fuse into helium. But what they do is they get two protons close enough that the odds of quantum tunneling together and forming helium become high enough that with 10 to the 50 particles smashing together inside of the sun, that quantum tunneling happens frequently enough to shine. And so quantum tunneling is a super important process, right? But yeah, so that's a separate thing. That's true that you can run through walls, but that's a quantum effect. And it's not 100 million. It's like 10 with like 100 million zeros or something.
Yeah, it's so
it's a number that's
small.
And it's because you're made out of 10 to the 23 particles, and so each of them have to do this at the exact same time. And for two sort of, if event is like a 1 in 1,000, for two things to happen at once is 1 in 1,000 times 1,000. So now it's 1 in a million.
Right.
For 10 to the 23 particles to do it to the ones, now we're talking about just 1,000 10 to the 23 times.
Got it.
And so now we're talking about 10 to the 69 zeros.
Yeah. So it is theoretically, mathematically possible, but extremely unlikely.
Yeah, exactly.
My friend, this was great.
This has been fun.
I can't thank you enough, Coop. And we were talking a little bit off camera. The next time we come in, Coop's going to bring 4 or 5 current happenings in science that are making the news.
Yeah, I'll try and break down some.
And you'll probably
some
debunk a lot of what we assume from clickbait and the rest of the nonsense that we deal with constantly. But
yeah, I would say that like we should have sort of like a hesitant optimism whenever reading any sort of like science article. That you have to understand that there's a sort of economic incentive to make if you're like reporting on science to make it seem amazing. And there are some truly amazing things out there, but we just have to be careful. Like, even with like the discovery of gravitational waves, that was like the biggest moment in my life. That was like so incredible whenever I saw that data for the first time. And like, we had the whole center of cosmology and particle physics where it was working. We had champagne, everyone was cheering. We had nothing to do with it. We were still cheering and like celebrating. But at the same time, like, a news article might say, like, now we can look back to the Big Bang. And it's like, well, wait a second.
It got distorted by the press and by media.
Exactly. It'd be like if whenever Galileo first looked through a telescope, we were like, now we will finally understand, like, black holes at the heart of the galaxy. It's like, no, it took us another 600 years.
Yeah, what a leap.
500 years, I say, before we were able to create the sort of, radio interferometers to look at black holes.
Doesn't make good press.
Yeah, it doesn't make good press. So I'll try and, like, sort of pour some cold water on something, but also get people excited.
I'm all right with that.
So
I appreciate it, Coop.
Cool. Yeah, always good being here.
Hey, good deal. Thank you, buddy.
Sure.
All right, we're out, friends. Thank you.